Now, I'm really curious how we take off from where we left off, where we were using this term exponential, but all we were doing was fiddling with areas. So how do we get there, and where is our magic formula?
So let's remember with sines and cosines and hyperbolic sines, we had these magic formulas. This exponential function that we defined also has a magic formula. I'll write it down for us just so that we can then explain it. It says if you, sort of like what we do with sine, what happens when you add two things and evaluate the function? The exponential is even simpler. You just get the exponential of the first guy multiplied by the exponential of the second guy.
Now, when we did it before with sines, we had this thin slice of pizza, and then we kind of pulled it over on top of the big slice.
We're going to do something similar here, except instead of a pizza slice, we're going to have a little vertical slice. So I'll make a slice here where the area inside here is this guy has area of x. That means this point here, it'll be exponential of what?
Well, of the area, so that's x.
Right. So this is exponential of x. Now what I want to do is I want to take that and slide it over here, except instead of using a rotation like we did with the circle, I'm going to use a special linear transformation that sort of stretches this out in the x direction and squishes it in the y direction.
You mean u.
Oh, the u direction. You're right, Matt. The u direction will get stretched out. The v direction will get squished down.
So we're just multiplying it by some scalings in u and v.
That's right. So if you wrote down the matrix, what I want to do is I want to expand in the u direction and squish in the y direction. And in these off directions, I just put a 0.
So what vector is that going to multiply?
Well, so for instance, this little vector here, this point 1, this is the vector 1, 0. If I put 1, 0 in here, I'm going to get the point exponential x0 and then 0. So this point
Gets mapped over to...
gets mapped over here, right? Now this point,
Yep.
this point here, okay, that's the point exponential of x. And when I multiply this out, I'm going to get a little product here.
So is that x or x0?
Ooh, that should be an x. And let's do a little bit of erasing since I'm going to be changing things around here. Thanks, Matt.
Yeah, so I saw that this point goes there, and this point's going to go somewhere else.
So I multiply this out, I get exponential of x0, exponential of x. So this is exponential of x0, exponential of x. And this, I multiply out 0 times 0 plus 0 times 0. This is 0. So this point gets mapped here.
Yeah,
So the special point exponential of x0 times exponential of x, right?
Yeah, absolutely. So we now know how this area gets squashed.
Now what happens to this guy? So this point here, we're not going to do the algebra, but it just gets squished over here to another part of the parabola, and its area is still x. Because this matrix, what's the determinant of this matrix?
It's 1, so areas are preserved.
Areas are preserved. So this long, skinny x area gets squished out into a sort of fat little area x. The total area here then is x naught plus x. And what we saw last time was that gives this point as being the point with the corresponding area. So this guy is equal to that guy, which is what we had here. So that's why this is true.
Oh, wow, that's really cool.
That's really cool.
That's really cool.
Now from this magic formula, this is how we get to see that this function, which we called exp, turns out to be an exponential function. Do you want to see that, Matt?
Sure.
Okay. Should I erase a little bit?
Yeah, what are you
Give
going to
myself a
erase?
little-
You can erase
Maybe
that
I'll
and
erase
keep
this.
that.
Yes, erase this. Okay. So let's look at this formula. Now let's do a simple example. Let's take exp of 1 plus 1. This is exponential of 1 times the exponential of 1 from our formula up here, right?
Which is the exponential of 1 squared.
Squared.
So what happens if you did it 1 plus 1 plus 1?
Well, I'm going to write this out. This exponential of 2 is the exponential of 1 squared.
So exponential of 3?
3.
Make
You
it a
get
3.
another one, so this would be a 3 here.
So whatever you put here is going to go there.
So this is going to say, in general, exponential of n for any integer is just exponential of 1 raised to the nth power.
Oh, that's very interesting. So now we start to see powers coming in.
You see powers. Now this is only for integers, but I could also do something like this. Exponential of a half. This is just some number. If I take a number and multiply it by itself, that's the same thing as taking the square root of the number multiplied by itself, right?
Yeah.
So if you think about this, this is just saying, okay, this is exponential of a half and a half, so I can add them together. That's exponential of 1 raised to the 1/2 power.
Oh,
So here I get a half, and I get a half there. You see a pattern?
yeah, that's very cool.
So let's jump ahead to what we think is the general result. If I take exponential of x, from these patterns here, what do you think that should equal in terms of exponential?
Where you had 2's, put in x's.
So I'll put exponential of 1 raised to the x power. So this is a very special number, exponential of 1. In fact, it's given the number e, defined as the number e, named after Euler. the nice
So
mathematician.
you've defined it, but where? How did you make this jump?
Well, we're seeing that there's a pattern. There's always exponential of 1. This number always comes up, and you raise it to a power. That gives us the exp at x. So this number e, this is where the exponential is equal to 1. So whatever area it takes to get an area of 1 here, this will give us exponential of 1, which is the special number e.
So actually, if you do this and find the area under this curve, you'll get a number close to 2.7 and so on.
That's right, because it's not too hard to see. It's not too hard to see that, okay, if I took the number 2 here, I get a little rectangular shape. This area's got to be less than 1. If I went all the way out to 3, I'm going to get something with area bigger than 1, just by a rough calculation. So E has to be somewhere between 2 and 3. It turns out to be that number there.
Oh, okay. So basically, you're computing this area and saying, hey, that corresponds to this number.
That's right.
And you're doing it just by the geometry of areas.
So we didn't do any limits. We didn't take anything going off to infinity. We're just saying a little bit of geometry.
And then the special magic formula closes the loop.
Exactly.
Because without that, we still could make arguments. But once we have this and this, we now have e to the x without limits.
So exponential of x, this special function that we define using only the hyperbola, is our function e to the x.
Wow, that deserves a superstar congratulations, Michael.
Thank you, Matt.